Hi guys. Today we're going to learn about magnetism. So the first thing you have to know about magnets is that every magnet creates magnetic fields that go in the opposite direction. These two sides are the same poles, so their magnetic field is pushing in the same direction. That's why when you push them together, they repel. However, if I flip one, this magnetic field will be pulling this one. So guys, magnetic fields come from moving charged particles. This is the basketball, and today it's going to represent a charged particle. So, when charged particles move like this and they spin, it creates a magnetic field. This magnetic field is a magnetic force that can act on other little objects. If I have a bunch of these charged particles spinning in the same direction, then it creates one big magnetic field and the object that it's in. So first, we're going to talk about how magnetic forces arise. But to demonstrate this, we're going to make it more simple by seeing how gravitational forces arise. When you have large, massive objects, like the Earth, it exerts a strong gravitational force on other objects. When you have charged particles that spin in a direction, they also create a magnetic force.
So Grant, why do apples fall from trees? Why don't they go up?
Well, Mike, you see, in everyday experiences, gravity has effect on you even if you're not in contact with it. If you have to fall from a tree, gravity is always acting on you even when the object's falling, just like this ball.
Oh. So right here we have an experiment that kind of demonstrates what Grant was saying, but in magnetic field terms. It demonstrates how two metals don't have to be in contact to show the power of a magnetic field. So here's another angle with the chain hanging from my hand, and it shows that the magnet is moving the chain with its magnetic fields even though it's not in contact with it.
So in this experiment, as Mike is showing here, it shows that gravitational forces are not as strong as magnetic forces.
Hey again. So, what is the difference between this and this? Why is this object magnetized, and why is this not? Nothing. Cut! So, actually, a magnet and a pencil both have the same components. This has charged particles, and this has charged particles also. However, the charged particles in this pencil are all going in different directions. They are all random, so all the magnetic fields cancel each other out. The charged particles in this magnet are all spinning in the same direction. Therefore, it creates one big magnetic field from all those charged particles. So, the next topic we will cover is called the right-hand rule. Now, what this is about is scientists need a tool to know the directions of the motion of a charged particle, the magnetic field that's acting on it, and the magnetic force. So, what's interesting about the direction of all of these, which is again the velocity of the charged particle, the magnetic field, and the magnetic force, is that the direction of all three of them are perpendicular to each other. So one would be going this way, the other would be going this way, and the other would be going out like that.
This right here is the mathematical equation for the right-hand rule, and it is magnetic field equals magnetic force on a charged particle over the magnitude of a charge times the speed of a charge. This equation shows is that all of these components are perpendicular to each other. In order to demonstrate the right-hand rule, if you take your right hand and curl your fingers in the direction that the earth spins while keeping your thumb extended, then your thumb points north. Likewise, magnetic north is defined the same way. So if you take your right hand and curl your fingers in the direction that the positive current flows, or the direction the positive charges are moving, then your thumb again points north. To dumb this down, we're going to use curse as an example. the magnetic field would point in this direction, and the velocity of the charge would go in this direction. This means that the magnetic force on a charged particle would be pointing this way.
You can see here we have the Earth's magnetic field pointing north in this direction, and the Earth's magnetic field south is pointing this direction. Now, a lot of people wondering what's the deal with that. Why do the needles point in these directions? The deal with that is that the magnetic pole located in the northern hemisphere is actually a south magnetic pole, and likewise, the magnetic north pole is located in the southern hemisphere. And so a lot of people wonder, well, why do we call it north if that's where a south magnetic pole is located? And it's really just an accident of history, and so many scientists just stuck with it for that matter. And there is actually the reason why the needle points in these directions either way is because there is actually the compass itself is magnetized, and so the needle itself is attracted to both the north and south sides either way regardless. Now, the reason why the north and south poles are always attracted by this needle is because there is a small magnet within the needles, and what the magnet is actually doing, it is actually interacting with the Earth's magnetic field, and the Earth's magnetic field is always, or most of the time, is usually really consistent, and so regardless, no matter whether or not, most of the time it will always be interacting with the north and south pole most of the time.
Well, what do you think will happen when I spin the compass? What should happen is that the red part should still point to the north side, and the white part should still point to the south side. Almost there. And hey, my hypothesis was correct. Alright, so what I have here is a little generator. Now, what this is a bunch of wire coiled around a tube, and the ends of the wire are attached to this mini light bulb. Now, the point of this experiment is to show that you don't need a battery supply to induce a current. All you need is magnets. What this demonstrated was that you don't need a battery to induce a current. What I had was these magnets inside this generator. Now, when the lights were off, what I did was I smashed this thing onto these two powerful magnets over here, and what that did was it changed the magnetic field acting on this coil over here. The overall effect of that was it induced a big current that would end up going through this light bulb over here and showing a red flash. So, this is a wire, and this wire has charged particles in it. Now, when I set this whole system in motion, the charged particles are moving, and it creates its own magnetic field. Actually, the magnetic field of the charged particles is strengthened by this iron rod in between. This wire also has charged particles, and when I move it, it creates its own magnetic field. However, because you have no iron rod, like in here, the total magnetic field is very weak. Therefore, you cannot even observe the result on the compass.
So in this experiment here, we're going to show how a current carrying loop produces a magnetic field. And this experiment was actually first proposed by a man named Hans Christian Ørsted. And so what he basically had here was he had two batteries, and what he had here was also a solenoid. And what solenoid is, it is basically a long, wound coil around insulated wire, and with any sort of iron or zinc or cobalt rod. It doesn't really matter which one you use, but either way, what the job of the solenoid is to strengthen the magnetic field, because without it, it doesn't really do much. So what we do here is we attach the ends of the solenoid to the batteries and wave the solenoid with the compass. You'll see that they actually the needle within the compass will actually move. So Ørsted's experiment was actually, his hypothesis was true, and that actually current carrying loop can produce a magnetic field.
Warning: if you're a compass, this may hurt to watch.